morning and welcome to the class. So, in the previous class I talked about fluorescence, what is fluorescence and all that. So, today I will be discussing mechanisms of fluorescence signaling systems, how on which mechanism they work and all that. So, first most important one we will be discussing first, that is called photo-induced electron transfer. Photo-induced electron transfer mechanism. In short, we say it is a PET mechanism. Okay. In a PET mechanism, what happens? We will mostly be discussing with spacer, okay, but that is equally applicable to integrated systems as well. So, like we have here receptor, spacer and fluorophore, receptor and fluorophore. Okay. Usually receptor we use, you have one or two nitrogens and they are attached to fluorophore, because you have to attach. This is a chemistry. So, you have to chemically attach. How we do that? A simplest kind would be suppose I make an aja crown kind of compound here, 1, 2, 3, say 4 and 5. This will be good for sodium ion, okay, size, because I have done the work on these things many times. So, I know that this will be a sodium ion receptor, and a spacer is methylene spacer. And what is a fluorophore? Usually we take multi aromatic systems. For example, we take anthracene. Anthracene is a very good fluorophore. Because a very good fluorophore is one double bond, then which one? This will be okay. Okay, this is okay. So, this is a fluorophore, this is an anthracene. Okay. So, so far we will be using only benzene ring, we will will do like this, okay, from now on, because of time shortage. So, what happens? This is a fluorophore and this is receptor. The receptor has nitrogen, has a lone pair. Remember, nitrogen will have a lone pair of electron, and this is easily can be reacted. For example, we take bromomethyl derivative of anthracene, 9 bromomethyl, 9 bromomethyl anthracene, okay, and here is NH. So, that NH can be replaced and it can go here and make this anthryl group is attached to this particular macrocycle. So, here is a fluorescent signaling system will work on PET process. So, let me describe the PET process now, and description will be quite easy if you take the frontier orbital diagram. So, my frontier orbital diagram, let me draw it here, then I will explain to you. Here is LUMO, lowest unoccupied molecular orbital. Here is HOMO, highest occupied molecular orbital. Here is HOMO and there is LUMO. Okay? This is of fluorophore. This is I am writing later, and this is HOMO of the receptor. So, this HOMO has mostly character of these two pair of electron pair on the nitrogen. So, electron pair on the nitrogen describe mostly the HOMO, highest occupied molecular orbital. So, I write 2 electrons. So, this is the beginning and HOMO has complete. Okay. So, this is my situation here, electron frontier orbital, LUMO is empty, HOMO has 2 electron and this HOMO of receptor, this is receptor and this is fluorophore. Okay. And spacer, in this case spacer actually work as a to transduce or to pass the information from one component to the other. All right. Now I excite my fluorophore. Okay. If it is since it is anthracene, so I excite it at a particular wavelength. I am not telling any wavelength or any numbers, they have no meaning now, but I will tell eventually. Okay. So, once you excite it, what will happen? This one of the electron will go here. Will go here. One electron goes from here to here after absorbing that energy with which I have excited the fluorophore. So, this side is empty, an orbital cannot, the HOMO cannot become singly occupied. Then what will happen? This electron pair from this HOMO of the receptor, that means nitrogen lone pair, one of the lone pair of nitrogen will come here. Okay, will come here. This process is called PET process, photo-induced electron transfer process. So, I will tell you again the situation. I have this compound and now I excite it. When I excite this fluorophore, it gives me this singly occupied LUMO HOMO, but it cannot remain singly occupied. So, from this HOMO of the receptor, that is a nitrogen lone pair, one of the electrons lone pair that will be donated to the HOMO. And what will happen? Electron at the LUMO from the fluorophore can slowly come, giving off radiation, okay, heat as in the form of heat to here. Okay, it will come here and then again we are back to the square one in the beginning. Okay. So, that what happened. But if I put a sodium ion here, I put a sodium ion here, what will happen? Sodium will engage the lone pair, because it will form chemical bond with here. Sodium will bind all. So, lone pair I will write here. So, what will happen then if I put sodium? This is energy, this is energy. If I put sodium ion, then this is LUMO, this is HOMO, of fluorophore, and HOMO will come here of receptor. Okay. Okay. HOMO will come down. Why? Because lone pair is now engaged to sodium ion. So, when the electron density is taken out from an orbital, its energy lowers, because it gets stabilized. All of you know this principle. Because its energy will go down, energy goes down below the HOMO of fluorophore. Okay? It goes below, because sodium ion will engage both this. Now, I excite the fluorophore. So, to the sodium complex, I excite the fluorophore. It goes like this. Okay. LUMO is now occupied. And how about this? Cannot go here. Why? Because it is already bound to sodium ion, already bound, engaged. It cannot go here. So, PET is not possible anymore. Okay? PET is not possible anymore, because this lone pair orbital is lower. From lower energy, electron cannot go to higher energy. That is point number 1. Point number 2 is this lone pair is engaged to sodium ion. So, it cannot donate. So, therefore, when I excite it now, this one of the electron goes to LUMO, but it cannot stay there. So, it comes out, comes down, giving me fluorescence, a strong fluorescence, So, this is the frontier orbital diagram of the PET process. So, basically, therefore, what is happening? If I look at it without considering this, whenever in a receptor spacer fluorophore system, my receptor is empty, but at that stage I excite the fluorophore, I do not see any fluorescence. Okay? No fluorescence, I do not see any fluorescence, because PET is operational, PET takes place. That is why I do not see any fluorescence. But when I have a sodium ion inside this macrocycle, then my lone pair, that is the HOMO of the receptor. So, my lone pair is engaged to sodium, it becomes stabilized and it becomes engaged to metal ion. So, PET is not possible, and therefore, I can see a large fluorescence. So, what happened? Happened is this, I make this system, I synthesize this system. Let me do it slowly. I synthesize this system. Okay. I synthesize this system and then excite the fluorophore, nothing happens because PET is operational. Now I put sodium, again excite this system, I see a strong fluorescence. That means when sodium enters here, I see strong fluorescence. So this is a microscopic scale, I cannot see it. In that microscopic scale, I find an analyte, in this case sodium ion. It enters and then I see a strong fluorescence peak. And if my macrocycle is empty, then if I excite, I do not see any fluorescence. That means this event of an analyte entering this receptor can be signaled by a strong fluorescence in a PET process. All right. So this is a very, very important phenomenon and very popular one. Okay. So I will show you. So now, therefore, what is important point? I have to synthesize a receptor. Let me go to the next step. I have to synthesize a receptor which is very specific for a particular metal ion. If I have to sense metal ion, sensing, I have to synthesize a macrocycle which is very selectively bind a particular metal ion. For example, this particular compound, okay, this is actually sodium. I will be writing for lithium, say. Okay. Now, so in this case, I am doing a integrated system. An integrated system I am writing. That one was sodium specific and this one is lithium specific. Okay. This one is a particular, this one is fluorophore and this is receptor. This receptor and fluorophore are integrated. Okay. And what is the name of this receptor? Receptor is, yes, I keep forgetting things. I have used it so many times and now I cannot. Receptor, okay. I am having Alzheimer's setting in. All right. This is a fluorophore, this is a receptor. Okay. Our job, a supramolecular chemist's job is to find a receptor specific for a metal ion. This particular receptor likes lithium ion. Lithium ion is very important. Why? For manic depression patient, okay, patients which are feeling always depressed. So lithium is a very important drug to fix that, but that drug can be administered. I cannot put lithium in kilos, then the person will die. But how much lithium? Lithium is an optimum within this window, 0.6 to 1.2 millimolar, millimoles, okay, 0.6 to 1.2 millimoles, and it depends upon the body weight of the person and all that. A small person which is feeling depressed, always depressed, always feeling bad, खराब लग रहा है, always, then if you give him lithium, we cannot give just lithium पानी में घोल के दे देंगे, no, we have to give it in a certain way, okay. Now, how much is lithium we have, we still can have? If we have some problem, then we administer lithium, but we want to know how much lithium we put inside, went in. Then we have to do fluorescence, okay. So, we have to take some sample out of that person, and then it has lithium. So, if we use this one, this particular system, okay, so then lithium can get in here, and it will show, because of this PET, it will show very strong fluorescence, okay. So, we can show these are lithium selective. So, what is the problem of chemist? Chemist problem is to design receptor specific for specific people. And how do you know the concentration? Concentration we know from the intensity of the lithium, okay, intensity of the emission. Say we can draw maybe like this a picture. It will be like this, lithium say 0.5, okay, it is here, intensity, and then here. So, if I say lithium is 2.0, then the 2.0, or maybe I will do it here, say 0.5, and here is 2.0. So, my fluorescence intensity of fluorescence, okay, intensity of fluorescence, if I take a fluorescence again and find its intensity here, okay, fluorescence is here, so intensity here, isko niche laga diya, that means we have given excess lithium 2.0. So, there is a problem, we cannot give excess lithium, we have to give around here when the fluorescence intensity is here. So, intensity, from intensity we can know approximately the concentration of the particular analyte, okay. So, intensity of fluor emission will give us an idea about concentration of the analytes. So, from intensity we can know that we are in the right range of 0.6 to 1.2 millimolar. So, these things are very, very important, all right. So, this is a lithium sensor, another lithium sensor, let me write, this is another lithium sensor. And here my fluorophore is naphthyl group. Me, this is my fluorophore. Okay. This is my fluorophore, and same thing is here also. Okay, these are two lithium sensor. This is important that we want a specific, because in our biological system we have sodium, we have potassium. Now, a manic depression patient is given lithium. So, only lithium should make complex, and if lithium makes complex, then what will happen? Then we can know its concentration from emission intensity, as simple as that. So, these are lithium sensors, and this is the principle from intensity. Then let us see about some other. So, now it will be very interesting. See, this particular, I told you that supramolecular synthon we can use as receptors. Now, here is a calixarine derivative. Calixarine derivative, here is a calixarine derivative. Okay. Drawing this is very difficult. Tertiary butyl, tertiary butyl. Then you have very difficult to draw these things, but anyway, we will try. Let me write this, at least shortcut. Okay. Let me draw this way. All right. And then it is bound. How these are bound? Anyway, these are bound. So, at the one end, okay, this is 1,2 alternate, 1,2 alternate calyx 4 arene. And once you make 1,2 alternate, why it will become 1,2 alternate? Because we derivatized it not with this propyl oxo species. Okay. So, T butyl groups flipped. So, 1,2 alternate, and we have a cavity here. This is NH. So, this is bound to fluorophore. Fluorophore is my, okay, I will write the fluorophore. I will not put that shortcut to you. Fluorophore is anthracene. Fluorophore is anthracene. Okay. So, in this pocket only lithium goes. So, I am just telling you different sensors. So, these are called sensors because they sense lithium. When a particular fluorescent signaling system can sense a particular analyte that is called a sensor for that analyte. So, here we have we are showing you the molecules designed as sensors for lithium ion, lithium plus sensors. Okay. And another krypton also I will show you. Another krypton I will show you before I end. Is a krypton, okay, and this krypton has methyl group. Methyl group, okay, it has a methyl group and dimethyl derivative, and another is anthracene. I told you that anthracene is a very popular fluorophore, and that is not very important whether we take anthracene or naphthalene or tetracene, does not matter, because they are only reporting, they are reporter, fluorophores are reporter. But what is important for chemist or rather supramolecular chemist is the design of these receptors to bring in specificity. So, these are specific for lithium ion. So, that is why they are important. So, this is the way we can get lithium sensors, all right. And whenever there is whenever I excite the fluorophore, I do not see any fluorescence, but when I put lithium in there, lithium, so nitrogen lone pair will be bound to lithium and PET will be blocked, PET blocked and I see fluorescence. PET is operational, I do not see any fluorescence. Okay. So, thank you for today's class. I have done lithium, and then similar way we can do sodium, potassium and so on. All right, thank you.